Welcome to Tech Explained. Today, we're really getting into the essential concepts you need for the AWS Solutions Architect Associate role. Think of this as your guide to understanding how you actually build those robust, scalable, and, efficient cloud solutions. Our goal here is to walk you through the core ideas and services, step by step, making sure you get a really solid grasp of the whole landscape.
Absolutely. And we want to explore not just what these pieces are, but really how they fit together, how they interact. We'll look at making smart decisions for different architectural challenges and, what really matters when you're designing things in the cloud. The aim is to make these sometimes complex ideas feel accessible, give you practical insights, things you can remember. You'll find out not just what the services do, but kind of why they're built the way they are and how that thinking impacts your work.
Okay, let's jump right in then. Segment 1, the foundations. Cloud computing and AWS itself. At the very heart of almost everything in the cloud is virtualization. To really get it, imagine you've got this big physical server, lots of CPU, memory, storage, network capacity. Now, picture logically slicing that up into smaller, totally independent units. Each one acts like its own virtual server, separate operating systems, separate applications. Isolated.
Exactly. And that flexibility is what gives the cloud its incredible agility, right? You can spin up a virtual server in seconds, run it just for as long as you need it, and then just shut it down. The resources go back into the pool.
Right. So it's efficient.
Hugely efficient. Better resource use, obviously. But also think about how easy it makes creating isolated environments. You need a sandbox for testing or maybe some experiments. You just create one. No waiting for hardware, no big upfront cost. That's a massive architectural advantage.
So for businesses, for developers, what are the really big wins here? We often hear about affordability, elasticity, scalability. What does that actually mean in practice?
Well, affordability comes from that pay-as-you-go model. You're not buying the whole server up front.
Like a utility bill.
Exactly. You pay for consumption. And elasticity means the resources can stretch and shrink automatically. Demand goes up. You get more resources. Demand drops. You release them. You don't pay for idle capacity.
And scalability ties into that.
Yeah, scalability is about being able to grow or shrink your whole infrastructure easily as your needs change over time. And this fundamentally changes IT spending. It moves away from those huge, risky capital expenditures.
Buying racks of servers, building data centers.
Right, all that upfront investment. Instead, it becomes flexible operational costs. You're renting capacity. And that frees up capital, reduces risk. It lets businesses innovate faster, respond to the market quicker. It's a huge business advantage.
Okay, let's zoom in on AWS specifically. Its structure is built on regions and availability zones. As an architect, what does that global setup mean when you're designing a solution?
Okay, so regions are distinct geographic areas. Think US East, Northern Virginia, or maybe Europe, Ireland. Totally separate. That separation matters for things like data sovereignty rules or maybe latency for users in that area, and definitely for disaster recovery planning.
And availability zones, AZs.
Right. Within each region, you have multiple availability zones, or AZs. An AZ is basically one or more discrete data centers. They have their own power, cooling, networking. They're physically separate within the region.
But close enough for low latency.
Exactly. Close enough for fast communication between them, but far enough apart that a fire or flood in one AZ isn't likely to take out another. This distributed design is key to AWS's high availability promise. If one AZ has a problem, your application can keep running from the others in that region.
Okay, so redundancy is built in geographically.
Precisely. And this leads straight into a critical concept.
Yep.
The shared responsibility model. You absolutely have to understand this. AWS is responsible for the security of the cloud.
Meaning the physical data centers, the hardware, the global network.
Yes, the underlying infrastructure. But you, the customer, are responsible for security in the cloud.
So that's my data, my applications, operating systems, network configurations, IAM permissions.
Exactly. You configure it, you secure it. Knowing where that line is drawn is fundamental for security and compliance.
Right. So we have this global infrastructure. Now, how do we actually interact with it? How do we get work done? AWS offers a whole suite of tools, doesn't it?
It does. A pretty comprehensive toolkit for managing multiple accounts, maybe across a large organization. There's AWS organizations. It lets you centralize billing, apply policies consistently, manage things together. Really useful.
And Control Tower builds on that.
Yeah, AWS Control Tower helps you set up a secure, well-architected, multi-account environment much faster using best practices and guardrails, sort of a landing zone accelerator. Then there's AWS Service Catalog. If you want to provide a curated list of approved IT services like pre-configured servers or databases to your internal teams, that's the tool.
Makes sense. What about compliance?
For compliance reports, like SOC reports or ISO certifications from AWS itself, you use AWS Artifact. It gives you on-demand access. Now, for the hands-on work, automation, the AWS command line interface, the CLI, and the software development kits, the SDKs, are vital.
For scripting and programmatic access.
Absolutely. Essential for automation. And finally, don't forget AWS support plans. If you run into trouble, need technical help or architectural guidance, there are different tiers available.
Good to know. Okay, what about moving existing stuff? Migrating from on-premises data centers to AWS, that sounds like a huge task.
It can be, yeah, but AWS provides services to help smooth it out. AWS Migration Hub acts as a central dashboard, gives you visibility, lets you track the progress of your different migration projects.
Kind of a control center for the move.
Exactly. Then for migrating the actual servers, physical or virtual, there's AWS Application Migration Service, often called MGN. It automates replicating your servers into AWS. If you're moving databases, AWS Database Migration Service, or DMS, is key. It helps migrate databases, even between different engines like Oracle to PostgreSQL, with minimal downtime. It handles schema conversion too.
That sounds powerful.
It is. And to figure out what you have on premises before you start, there's AWS Application Discovery Service. It helps gather data about your servers, their dependencies, helps you plan the migration. These tools are really the scaffolding you need for a successful transition.
All right, foundations covered. Let's move into the core compute services. The engine room, as you said, Amazon EC2, Elastic Compute Cloud. These are the virtual servers. When I need one, how do I choose? What are the first steps?
Okay, it starts with the Amazon Machine Image, the AMI. Think of the AMI as the blueprint, the template for your instance. It bundles the operating system, maybe some pre-installed software, all configured on the root volume.
And I have choices for AMIs.
You do. There are Amazon Quick Start AMIs. These are official supported images for common OSs like Linux, Windows, even Mac OS now. Or you can look at the AWS Marketplace. Lots of third-party vendors offer AMIs there, often pre-configured with specific applications ready to go.
Okay, I've picked my OS and software blueprint with the AMI. What's next?
Next, you choose an instance type. This is really critical from an architectural standpoint. The instance type defines the hardware resources. How many virtual CPUs, how much memory, the type of storage attached, the network performance.
So matching the instance type to the workload is key.
Absolutely key. The combination of AMI and instance type directly dictates performance, efficiency, and cost. It's all about right sizing.
Makes sense. Now, beyond the instance itself, applications need persistent storage for data. That's where EBS comes in, right? Elastic Block Store.
Exactly. EBS volumes provide that persistent block-level storage you attach to your EC2 instances. The keyword is persistent. Unlike instance store volumes, which are temporary and disappear if the instance stops, EBS volumes stick around. Your data is safe.
And there are different types for different needs. You mentioned performance earlier.
Yes, several types. For really demanding applications needing high IOPS input-output operations per second or high throughput, you'd look at provisioned IOPS SSD volumes. Those are IO1, IO2, and the really high-end IO2 Block Express.
And the value there is consistency.
Consistency and guaranteed performance. Databases, transactional systems, they need predictable I/O. Provisioned IOPS gives you that service-level agreement for performance. IO2 Block Express, for instance, can hit, I think, up to 256,000 IOPS per volume. Huge numbers.
Wow. Okay, what about backups?
That's another crucial EBS feature, snapshots. You can take point-in-time snapshots of any EBS volume. These snapshots are stored durably in S3 and are perfect for backups or for creating new volumes or even creating new AMIs from an existing instance's state.
And security, encryption.
Yes, very important. EBS volumes can be encrypted both at rest, on the disk, and in transit as data moves between the instance and the volume. This uses AWS Key Management Service, KMS, so you have control over the encryption keys.
Okay, that's storage attached to the instance. Now let's talk about handling fluctuating demand. EC2 auto-scaling. This sounds really powerful for managing costs and performance.
Oh, it's fundamental to cloud-native architectures. Auto-scaling lets your EC2 fleet automatically grow or shrink based on demand. It means you always have enough capacity, but you're not paying for idle servers during quiet times.
So how do you tell it what kind of instance to launch?
You define that using either a launch configuration, which is the older way, or more commonly now, a launch template. Launch templates are more flexible. They support versioning. You can use them for more than just auto-scaling. Generally the way to go.
And how does it know when to scale?
That's based on scaling policies, which are usually tied to CloudWatch metrics. You can have simple scaling, add X instances if CPU goes above Y%, or step scaling, which adds capacity in increments. Or target tracking, which is probably the most common. You set a target, like keep average CPU utilization around 50%, and auto-scaling handles adding or removing instances to maintain that target.
Like a thermostat for your servers?
Exactly like that. Very efficient, very hands-off for managing dynamic loads.
Managing lots of instances sounds like it could get complicated, though. Patching, configuration. What tools help streamline those operations?
That's where AWS Systems Manager really comes into its own. It's a suite of tools for operational management. It groups capabilities into actions and insights. Actions let you perform bulk operations. These are defined in documents. Automation documents for things like patching AMIs across multiple instances, or command documents for running specific scripts.
So you can manage fleets of instances together.
Precisely. A really key component is Session Manager. It gives you secure, interactive shell access bash or PowerShell directly to your instances through the console or CLI.
Without opening SSH ports.
Exactly. No open inbound ports, no managing SSH keys. It's a massive security improvement. Then there's Patch Manager, which automates patching using defined patch baselines. And State Manager helps ensure your instances stay in a desired configuration state over time, running checks and applying configurations automatically. You can even collect software inventory.
Okay, that covers traditional VMs. What about containers? They're a big deal now for lightweight compute.
Huge deal. Containers offer great resource utilization, portability, fast deployments. AWS has several services for them. Amazon Elastic Container Service, ECS, is a fully managed orchestration service. You define your containerized application. ECS manages the cluster, instances, networking.
But you still manage the underlying EC2 instances.
With ECS on EC2, yes. But there's also AWS Fargate. Fargate is the serverless option for containers. You just define your container, ECS or EKS schedules it on Fargate, and you don't see or manage any underlying servers at all. You pay per container resource usage.
So totally abstracted infrastructure.
Completely. If you're using open source Kubernetes, there's Amazon Elastic Kubernetes Service, EKS. It provides a managed Kubernetes control plane integrated with AWS. And for hybrid scenarios, ECS Anywhere lets you extend ECS orchestration to manage containers running on your own on-premises servers too.
Lots of options for container workloads then.
Definitely. You can choose the level of abstraction and control that fits your needs.
All right, let's switch from compute to AWS storage. Amazon S3 Simple Storage Service is probably one of the most well-known AWS services. It's not like a regular file system, is it?
Not at all. It's object storage designed for internet scale. You store objects files essentially inside buckets. And bucket names have to be globally unique across all of AWS. That's an important point.
Globally unique. Wow.
Yeah. And inside the bucket, it's a flat structure. You don't have traditional folders. You can use prefixes in your object names like images logo.jpg to simulate folders, which helps with organization and querying. But fundamentally, it's flat.
And it's known for durability and availability.
Extremely high durability and availability. S3 standard is designed for 11 nines of durability, 99.9999999%. Basically, you're incredibly unlikely to lose data. And high availability means you can access it when you need it.
What about managing objects over time? Backups, cost savings?
Two key features there: versioning and lifecycle management. Versioning keeps old copies of objects if they're overwritten or deleted. Fantastic protection against mistakes. Lifecycle management lets you define rules to automatically move objects between different storage classes or delete them after a certain time. Great for cost optimization and compliance.
You mentioned storage classes. S3 seems to have quite a few, each with different costs and access speeds. How do you navigate that?
That's a really important optimization area. You have S3 standard for frequently accessed data, fast, reliable, then S3 standard infrequent access, standard IA. Cheaper storage cost, but a small fee when you retrieve data. Good for less frequent, but still fast access. S3 one zone IA is even cheaper, but stores data in only one availability zone, so there's less redundancy. Good for reproducible data you access infrequently.
Okay. What about automating the tiering?
That's S3 intelligent tiering. It automatically monitors access patterns and moves your data between frequent and infrequent access tiers for you. No manual work, great cost optimizer.
And for really cold data, archiving?
That's Amazon S3 Glacier and S3 Glacier Deep Archive. These are the absolute lowest cost options. But retrieval isn't instant. It takes minutes for Glacier, potentially hours for Deep Archive. Perfect for long-term archival where retrieval time isn't critical. Choosing the right class really depends on how often you access the data and how quickly you need it back. Big impact on cost.
Makes sense. So data's in S3. How do you control who gets to access it? And how do you speed up transferring really large files?
Access control is key. You primarily use either S3 bucket policies or IAM policies. These JSON policies define exactly who, which principal can perform what actions, like get object, put object, on which resources, the bucket or specific objects. Very granular control. A newer feature is S3 access points. These are dedicated network endpoints for your bucket, each with its own policy. Makes managing access for different applications or teams much cleaner, especially at scale.
Okay. And speeding up uploads.
For large files, especially over long distances, S3 transfer acceleration is the way to go.
Sure.
You enable it on the bucket, and then uploads get routed through nearby AWS EDS locations and travel over Amazon's optimized backbone network to S3.
Bypassing the public internet congestion.
Exactly. It can significantly speed things up.
What if the files are really massive, like petabytes? Internet transfer might just be impractical.
Right. For those huge data sets, you use the AWS Snow family.
Yeah.
Physical devices AWS ships to you. There are Snowball Edge rugged devices for terabyte or petabyte scale transfers. They often have compute capabilities too for some edge processing. And for exabyte scale, that's 1,000 petabytes. There's Snowmobile. It's literally a shipping container on a truck.
A truck full of data.
Pretty much. You load your data onto the device at your site, ship it back securely, and AWS loads it into S3 for you. Highly secure, very efficient for massive offline transfers.
Incredible. Okay, let's move into networking within AWS, the virtual private cloud, or VPC. It's like your own private network space in the cloud.
That's a great way to think about it. A VPC is your logically isolated section of the AWS cloud. You launch your resources into it. You define its IP address range using CIDR notation, like 10.0.017. That sets the boundary.
And inside the VPC.
Inside, you create subnets. These are ranges of IP addresses within your VPC, again defined by CIDR blocks, like 10.1.1.024. Each subnet lives entirely within one availability zone. And crucially, subnet CIDR blocks within a VPC cannot overlap.
Any reserved addresses.
Yes. AWS reserves the first 4 IP addresses and the last IP address in every subnet for its own networking purposes.
Yeah.
Good to remember when planning. And you always have to assign an IPv4 CIDR block, even if you plan to primarily use IPv6.
Got it. So we have the VPC, the subnets. How do things inside talk to each other, and how do they talk to the outside world?
Several components make that happen. Elastic Network Interfaces, or ENIs, or the virtual network cards attached to your instances. They enable communication. Then you have route tables. Every subnet is associated with a route table, which defines where network traffic from that subnet should go.
Like a roadmap for packets.
Exactly. There's always a local route that allows instances within the VPC to talk to each other directly using their private IPs. To reach the internet, you add a default route, 0.0.00, that points to an internet gateway.
And that makes a subnet public.
Right. A subnet whose route table has a route to an internet gateway is considered a public subnet. Instances in it can potentially get public IPs and communicate directly with the internet. Subnets without that route are private subnets. Instances in them can't reach the internet directly.
Okay, you mentioned gateways. Internet gateway connects to the internet. What other kinds are there?
Good question. For instances in private subnets that need to initiate outbound connections to the internet, maybe for software updates, but shouldn't be reachable from the internet, you use a NAT gateway.
Network address translation.
Exactly. Or an older approach was using a NAT instance, basically an EC2 instance doing NAT. NAT gateway is the managed, more scalable service now. To connect your VPC back to your on-premises network securely over a VPN, you use a virtual private gateway, VGW. And if you have lots of VPCs or VPCs and on-premises networks you want to connect together, a transit gateway acts as a central hub, Cloud Router. Simplifies complex network topologies immensely.
Makes sense. Let's talk network security within the VPC, security groups and network ACLs. How do they work and what's the difference?
2 key layers of defense. Security groups act as firewalls for your EC2 instances. They operate at the instance level. They're stateful, meaning if you allow outbound traffic on port 80, the return traffic is automatically allowed back in. You don't need a separate inbound rule for the response.
That sounds convenient.
It is. They use a default deny approach for inbound traffic. Everything is blocked unless you explicitly allow it. Network access control lists, or NACLs, operate at the subnet level. They act as a firewall for all traffic entering or leaving a subnet. and ACLs are stateless. If you allow inbound traffic, you must also explicitly allow the outbound return traffic, and vice versa.
More configuration work then.
A bit more, yeah. And the rule order matters in NACLs. Rules are evaluated in numerical order, and the first matching rule, allow or deny, is applied. So a lower numbered deny rule can block traffic, even if a higher numbered allow rule exists. They offer very granular control, but require careful setup.
So security groups for instances, NACLs for subnets, stateful versus stateless. Got it. What about connecting securely back to on-prem beyond just VPNs and controlling instance placement for performance?
For a dedicated private connection from your data center to AWS, bypassing the internet, you use AWS Direct Connect. It offers consistent performance, lower latency, potentially higher bandwidth than VPNs. You can get hosted connections through partners or dedicated circuits direct from AWS.
And how does that connect into the VPCs?
Direct Connect uses virtual interfaces, VIFs. A private VIF connects to your VPC via a virtual private gateway. A public VIF lets you access public AWS services. A transit VIF connects to a transit gateway. Direct Connect gateways let you associate a single Direct Connect connection with multiple VPCs, even across regions.
Okay. And placement groups?
Placement groups give you control over how your EC2 instances are physically placed within AWS infrastructure. 3 types. Cluster placement groups pack instances close together in one AZ for low latency, high throughput networking. Good for HPC. Partition placement groups spread instances across different logical partitions on different racks within an AZ. Reduces correlated hardware failure risk for things like Hadoop or Cassandra. Spread placement groups place each instance on distinct underlying hardware, potentially across AZs. Maximum protection against simultaneous failures for critical apps.
Interesting. So you can fine-tune placement for performance or resilience.
Exactly. It's an advanced option for specific workload needs.
All right, let's shift to databases, a core part of almost any application. AWS offers relational and non-relational options. What's a fundamental difference an architect needs to understand?
It really boils down to the data model and what they're optimized for. Relational databases, often used for OLTP, online transaction processing, structure data in tables with predefined schemas and relationships. Think SQL databases like MySQL, PostgreSQL. They excel at ensuring data consistency, ACD properties, and handling frequent small transactions. Good for traditional business apps.
And non-relational, NoSQL.
Non-relational or NoSQL databases like DynamoDB are much more flexible. They handle unstructured or semi-structured data key value pairs, documents, graphs. They're typically optimized for massive scale, high speed, and specific query patterns, often trading some query flexibility or immediate consistency for that performance. You also hear about OLAP, online analytical processing databases, which are optimized for complex analytical queries on large data sets, like data warehouses.
So the choice depends heavily on the application's needs, data structure, scale, query patterns.
Absolutely. It's a foundational architectural choice. Relational for structure and consistency, NoSQL for flexibility and scale, generally speaking.
Amazon RDS, Relational Database Service, makes running those traditional databases easier, right? Takes away the operational burden.
Hugely so. RDS is a managed service. It handles patching, backups, scaling, provisioning for you, lets you focus on your application. It supports popular engines, MySQL, PostgreSQL, MariaDB, Oracle, SQL Server, and also Amazon Aurora, which is AWS's own highly performant MySQL and PostgreSQL compatible engine.
How do you configure it for performance and reliability?
You choose an instance class, standard, memory optimized, burstable, based on CPU memory needs, and storage type, SSD or older magnetic. For high availability, you enable multi-AZ deployment. RDS synchronously replicates your data to a standby instance in a different AZ. If the primary fails, it automatically fails over. Minimal downtime, no data loss.
And for scaling reads?
You can create read replicas. These are asynchronous copies of your primary database. You direct read traffic to them to offload the primary. They can be in the same region or different regions. They can also be promoted to a standalone database for disaster recovery, but because replication is async, there's a small potential for data loss if the primary fails suddenly. And RDS handles automated backups and point-in-time recovery too.
Okay, what about the NoSQL side? DynamoDB for scalable, fast databases. How does that work architecturally?
DynamoDB is fully managed, designed for single-digit millisecond latency at massive scale. Really impressive performance. Data is stored as items, which are collections of attributes, key value pairs. Items are identified by a primary key. It can be a simple primary key, just a partition key or hash key, which determines data placement. Or a composite primary key, partition key plus sort key, which allows more complex querying within a partition.
And you mentioned attributes have types.
Yeah, scalar types like string, number, Boolean. set types for lists of unique values, and document types for nested JSON-like structures. Very flexible schema. A key concept is provision throughput. You tell DynamoDB how many read capacity units, RCUs, and write capacity units, WCUs, you need per second.
So you pay for the capacity you reserve.
Exactly. You can also use on-demand capacity now, but understanding provision throughput is important. Another consideration is read consistency. Strongly consistent reads guarantee the absolute latest data, but use more capacity and might be slightly slower. Eventually, consistent reads are faster, use less capacity, but might return slightly stale data for a brief moment after a write.
So another trade-off based on application needs.
Always trade-offs in architecture.
Moving databases is often painful. How does AWS Database Migration Service, DMS, help?
DMS makes it much, much easier. It facilitates migrating databases to AWS, or even between different database engines within AWS with minimal downtime. It handles both homogeneous migrations like Oracle to Oracle and RDS, and heterogeneous migrations like SQL Server on-prem to Aurora PostgreSQL.
How does it work?
It provisions a replication instance, which is basically an EC2 instance managed by DMS. This instance connects to your source and target, handles the data replication, and even does schema conversion for heterogeneous migrations. For really huge databases, you can even use it with Snowball Edge for the initial offline data load. It takes a lot of the pain and risk out of database migrations.
Great. Now let's talk security fundamentals. Identity and access management, IAM. This controls who can do what, right?
Absolutely fundamental. IAM is how you manage your principals, users, groups, and roles, and control their permissions to AWS resources. Permissions are defined in IAM policies. These are JSON documents specifying what actions, like EC2.start instances, are allowed or denied on which resources, like a specific EC2 instance ARN, may be under certain conditions, like source IP address.
And the default is no access.
Default, deny. Principals start with 0 permissions. They only get access through attached policies. This forces you towards the principle of least privilege.
Granting only the permissions needed, nothing more.
Exactly. It's crucial for security.
So tell me more about those principles. Users, groups, and roles. How do they differ?
Okay, IAM users typically represent individual people or applications needing long-term credentials. Password for console, access keys for API. IAM groups are just collections of users. You attach policies to the group, and all users in that group inherit those permissions. Much easier to manage than assigning policies individually. IAM roles are really powerful. They grant temporary permissions. Instead of giving an EC2 instance or Lambda function permanent keys, you assign it a role. The service then assumes that role and gets temporary credentials. Much more secure. Roles are also used for cross-account access or federated access from external identity providers.
So roles are for services or temporary access?
Primarily, yes. Always aim for roles over long-lived user keys where possible. Again, least privilege is the goal. Access keys are those programmatic credentials, ID and secret key, used for CLI SDK access.
Are there other AWS services for identity beyond the core IAM?
Yes, several. Amazon Cognito is for managing user identity and authentication for your mobile and web apps. Think user sign-up, sign-in, social federation. AWS Managed Microsoft AD lets you run actual Microsoft Active Directory as a managed service in AWS, or connect to your existing on-prem AD. AWS Single Sign-On, SSO, provides a central place to manage access across multiple AWS accounts and even cloud applications like Salesforce or Office 365. User sign in once.
And for keys and secrets?
AWS Key Management Service, KMS, is for creating and managing encryption keys used across many AWS services. AWS Cloud HSM provides dedicated hardware security modules if you need Fix 142 Level 3 validation. And AWS Secrets Manager helps you manage, retrieve, and automatically rotate secrets like database passwords or API keys used by your applications. Avoids hard-coding secrets.
Okay, lots of tools for identity and access. Now monitoring, knowing what's happening. You mentioned a triad, CloudTrail, CloudWatch, AWS Config.
Right. These three give you comprehensive visibility. CloudTrail is the audit log, who did what, when, and from where. Every API call. CloudWatch is for performance metrics and logs. How are my resources performing? What are my applications logging? AWS Config tracks resource configurations and changes over time. What did my environment look like, and how has it changed? Is it compliant?
Let's break those down. CloudTrail first, the audit trail.
Think of it as the security camera recording every action. It logs events, API calls made by users, roles, services. Management events track resource changes. Create instance, delete bucket. Data events track object-level activity. S3 gets butts, DynamoDB item access. Invaluable for security investigations, troubleshooting operational issues caused by changes, and compliance audits. Logs go to S3, can be sent to CloudWatch logs too.
CloudWatch then. Metrics and logs.
CloudWatch collects time series data points metrics from AWS resources, CPU, network disk I/O, and custom sources. You can graph these metrics, analyze trends, use metric math to derive new metrics like error rates. CloudWatch alarms let you set thresholds on metrics. If a threshold is breached, it can trigger notifications, SNS, or actions, auto-scaling, and logs. CloudWatch logs ingests, stores, and monitors log files from EC2 instances via an agent, Lambda, CloudTrail, lots of sources. You can search logs, create metric filters to extract data from log events and turn it into CloudWatch metrics, set retention periods. Logs are organized into log groups and log streams.
Okay. What about Amazon Event Bridge? How does that fit in? It sounds like reacting to things happening.
It is, but it reacts to events, not metric thresholds like CloudWatch alarms. An event is a notification that something changed stop. An EC2 instance stopped. A file landed in S3. A security finding occurred. Event Bridge monitors, event buses. There's a default one, plus you can create custom ones. Rules match event patterns. When a rule matches, it sends the event to targets, Lambda functions, SQS queues, SNS topics, many others. It's key for building event-driven, decoupled architectures. Also handles schedule events, like cron jobs.
So reacting to specific occurrences rather than performance levels.
Exactly. More about choreography than threshold monitoring.
And the third part of the triad, AWS config, tracking configuration changes.
Right. If CloudTrail is what happened, config is what did things look like?
Yeah.
It records the configuration state of your resources over time. It creates a configuration history with configuration items detailing each resource's settings at different points. Lets you see how things were configured in the past, how they relate.
Useful for compliance.
Very much so. You can define config rules managed by AWS or custom to check if your resources comply with your policies, e.g. are all my EBS volumes encrypted. It alerts you to non-compliant resources, can also record software inventory on instances. Config history goes to S3 via a delivery channel.
Okay, that monitoring triad seems incredibly powerful together. Let's move to DNS and content delivery. Amazon Route 53. This is AWS's DNS service.
Yes, highly available, scalable DNS. It does domain registration, manages DNS routing via hosted zones, and performs health checks on endpoints. Inside a hosted zone, you create record sets, A records for IPv4, CNAMEs for aliases, etc. A really useful AWS-specific feature is alias records. They let you point a domain name, like www.example.com, directly to AWS resources like load balancers, CloudFront distributions, or S3 websites.
How are they different from CNAMEs?
They work at the apex domain, example.com, not just www.example.com, which CNAMEs can't. And DNS queries to alias records pointing to AWS resources are free. Plus, they automatically track IP changes of the target resource.
Nice. And Route 53 does more than just name to IP mapping. Routing policies.
Oh yeah, it's very smart about routing traffic. Simple routing is just one resource. Weighted routing distributes traffic by percentage, good for A/B testing. Latency-based routing sends users to the AWS region with the lowest latency for them. Failover routing uses health checks to send traffic to a backup if the primary fails. Geolocation routes based on user's country continent. Geoproximity routes based on distance with optional bias. And multi-value answer returns multiple healthy IP addresses, letting the client choose one. Lots of options for performance and resilience.
Okay, so Route 53 gets the user pointed in the right direction. How do we make sure content gets delivered fast globally? That's CloudFront, the CDN.
Exactly. CloudFront is Amazon's content delivery network. It caches your content, static files, dynamic content video at edge locations all around the world, close to your users. When a user requests content, CloudFront serves it from the nearest edge location, drastically reducing latency.
Where does it get the content from originally?
From an origin you define. That could be an S3 bucket, an EC2 instance, a load balancer, or even a non-AWS server. You configure a distribution in CloudFront to specify the origin, caching behavior, security settings like HTTPS, etc. It can also compress files automatically to speed things up further.
So it speeds things up and reduces load on the origin servers.
Correct on both counts. Essential for global applications.
Let's talk big data. Organizations have data everywhere. How do data lakes help? And what's AWS Lake Formation?
Data lakes address the problem of data silos. It's a centralized repository where you can store vast amounts of structured and unstructured data as is without needing to define a schema up front. AWS Lake Formation helps you build and secure these data lakes much more easily. It automates many steps like data ingestion, cataloging, cleaning, and setting up fine-grained access controls.
And the benefit is querying everything together.
Yes, you can then use various analytics services, Athena for SQL queries on S3, QuickSight for BI, Redshift Spectrum, Glue to analyze the data in place, imposing schema on read. Very flexible for exploration and analysis.
What about processing data in real time as it streams in, the Kinesis family?
Right, Kinesis is for streaming data. There are a few variants. Kinesis Video Streams is specifically for time-encoded data like video, audio, radar. Kinesis Data Streams is for ingesting large streams of generic binary data, logs, clicks, IoT data. It stores data in shards for a period, default 24 hours up to a year, allowing multiple independent applications to consume and process the stream concurrently. Good for fan-out scenarios. Kinesis Data Firehose is simpler. Its job is to capture streaming data, optionally transform it, for example, convert formats, batch it, and reliably deliver it to specific destinations like S3, Redshift, Elasticsearch, or Splunk. Less flexible consumption, but easier delivery setup.
So data streams from multiple consumers, Firehose for simple delivery.
That's a good way to summarize the core difference.
Data often needs cleaning or reshaping before analysis. ETL extract, transform, load. How does AWS Glue help with that?
Glue is AWS's serverless ETL service. It takes away the need to manage ETL infrastructure. It has a data catalog, which it can populate automatically by crawling your data sources, S3, RDS, etc., to discover schemas. This catalog provides metadata for ETL jobs and query engines like Athena. The ETL jobs themselves run on a managed Apache Spark environment. You can define jobs using a graphical interface or by writing Python Scala scripts. It handles the provisioning and scaling of the Spark cluster for you. Makes complex transformations on large datasets much easier.
Serverless ETL sounds good. Okay, let's move to the final big section. Architecting for specific requirements, pulling everything together. First up, resilient architectures, keeping things running.
Resilience is key. Designing systems that can withstand failure. We talk about nines of availability. Core strategies involve redundancy across multiple availability zones, spreading EC2 instances via auto-scaling groups across AZs, using RDS multi-AZs, even multi-region architectures for the highest levels of resilience. S3 provides inherent durability and versioning, EBS snapshots for backups.
And decoupling components.
Absolutely vital. Using services like SQS, Simple Queue Service, for message queues, and SNS, Simple Notification Service, for pub-sub messaging. If one microservice fails, messages can queue up in SQS, and the system doesn't grind to a halt. Decoupling prevents cascading failures. Route 53 health checks and failover routing also play a big role, automatically redirecting users away from unhealthy endpoints.
It's about removing single points of failure at every layer.
Exactly. And having recovery strategies planned, knowing your RPO, recovery point objective, how much data can you afford to lose, and RTO, recovery time objective, how fast do you need to recover.
Okay, beyond just staying up, high-performing architectures, making things fast and efficient.
Performance optimization involves choices across the board.
Yep.
Compute, picking the right EC2 instance types, using auto-scaling effectively, considering serverless, Lambda, or containers, ECS Fargate for certain workloads. Storage, choosing the right EBS volume types, like provisioned IOPS, SSEs, using the right S3 storage class, and critically, implementing caching.
Caching like Elasticache.
Yes, Elasticache, for Redis or Memcached, to cache database query results or session data in memory for super fast access. And CloudFront for caching content at the edge. Caching is often the biggest performance booster. Networking, using instances with enhanced networking, INI-IFA, leveraging VPC endpoints for private connections to AWS services, using the right type of load balancer, application load balancer for L7, network load balancer for L for extreme performance. And using infrastructure as code, like CloudFormation, helps deploy performant architectures consistently and manage updates reliably using change sets. Continuous monitoring with CloudWatch and load testing are also crucial to find and fix bottlenecks.
Next, secure architectures, protecting assets, always top of mind.
It has to be. Starts with the CIA triad, confidentiality, integrity, availability, and the shared responsibility model. IAM is the foundation. Least privilege, strong policies, using roles effectively. Network security. Security groups, stateful, instance level, and NACLs, stateless, subnet level, to control traffic. Auditing and detection. CloudTrail for API logs, CloudWatch logs, plus Athena for analysis. Services like GuardDuty for intelligent threat detection, Inspector for vulnerability scanning, Detective for investigation.
What about protecting against attacks?
AWS Shield. Standard is free, advanced is paid. for DDoS protection, AWS WAF, Web Application Firewall, to filter malicious web traffic like SQL injection or cross-site scripting. And encryption is non-negotiable. Encrypt data at rest, using KMS with S3, EBS, RDS, etc., and in transit using TLS HTTPS. Amazon Macie helps discover and protect sensitive data in S3.
Security needs to be layered throughout the design.
Absolutely. It's not an afterthought, it's built in.
Finally, cost-optimized architectures. Cloud is pay-as-you-go, but costs can add up. How do you design for efficiency?
Proactive cost management is essential. Use AWS budgets to set alerts. Use Cost Explorer and cost and usage reports to understand where money is going. AWS organizations for consolidated billing. For compute. Right-size your instances. Use auto-scaling. Consider containers or serverless. And understand the pricing models.
On-demand reserved instances spot.
Right. On demand for flexibility. Reserved instances, or savings plans for predictable workloads, offer significant discounts, up to 70-75% for 1 or 3 year commitments. Savings plans are more flexible than standard RIs. Spot instances offer the deepest discounts, up to 90%, but can be interrupted. Great for fault-tolerant, non-critical workloads like batch processing or testing. Using the right model for the right workload is key. Storage. Use the right S3 storage class, standard IA, one zone IA, Glacier for colder data. Use lifecycle policies to automate tiering. Databases. Choose the right RDS instance size. Manage DynamoDB throughput carefully. Provision versus on-demand. Networking. Use CloudFront to reduce data transfer out costs. Use VPC endpoints where possible. It's about making conscious choices everywhere to align spending with value.
Wow, we've covered a huge amount of ground there. From the absolute basics of virtualization and cloud through core services like EC2, S3, VPC, RDS, IAM, monitoring tools, all the way to architecting for resilience, performance, security, and cost. It really gives you a comprehensive picture of the building blocks and the thinking needed for the solutions architect associate role.
I think the main thing to remember is that it's not just about knowing individual services. It's about understanding how they fit together to solve problems, how to meet those non-functional requirements, availability, speed, security, while keeping an eye on the cost. It really is about thinking like an architect, balancing those trade-offs constantly, and knowing that the landscape is always evolving.
That's a great way to put it. So as you, our listeners, continue exploring AWS, maybe think about this. How does understanding these principles change how you might tackle complex problems, even outside of tech? What was the one concept today that really clicked or stood out for you?
Keep exploring, keep asking questions, and definitely keep building. Thanks for tuning in.
Until next time, keep learning and innovating.